So last time we just talked about Boolean algebra. Algebra means you get different objects. You want to, you know, do different operations between them. Basically, we can add, we can subtract, we can multiply, we can uh, divide uh, for the numbers. For the sets, we can take the union, we can take the intersection, we can take the complement and so on. So these are different operations for different objects. And if you compare the algebra of numbers with the algebra events or sets or Boolean algebra, you can see some common features or laws that apply to both, like the addition in numbers corresponds to the union between the sets, and the multiplication in numbers corresponds to intersection of sets. And if you do this correspondences between numbers and the sets, then you see, the uh, distributive law, the commutative and associative laws hold for both. If you just change, those union intersection into addition and multiplication. So this is the one thing that we can use when we try to simplify the algebra or expressions involving sets or events in here. But not all of them are working the same way as numbers. Like we got some properties of events or sets do not work in the same way as numbers. Some of them do, but not all of them. But in any case, we can use all of those results. Either they are, similar to algebra in numbers, or they're not. We still have those rules that we can use when we try to simplify or prove some results in Boolean algebra. And we just did one example last time. We're going to do a little more so you can see how we can use this kind of algebra in in our sets or events. So in this problem example, we need to show these two sets are equal. A union B intersecting with A union C is equal to A union B intersecting C. We can use the approach before we did. You can pick up an element on the left and show that element is also an element of the right side set. And then you pick up one element from the right side and show it's also an element of the left side set. And because the picking is random, then you can essentially show these two sets are equal. We did some examples before. But there's an easy way to do it. If you just change the union to addition and the intersection to multiplication, then this just becomes a product of addition of two sets. If you think a binomial, times a binomial. So you can do the same thing as you do with numbers. You can FOIL them. So what you get is A plus B times A plus A plus B times C. Okay. Well, you just keep doing this FOIL, and you get AA plus BA or AB since multiplication or intersection of two sets or commutative, right? And plus a theta plus bc. Well, a is just equal to a if you still remember. Intersecting a with itself, we get a, and that's just same as a intersecting with a omega. Where omega is the universal set or the sample space we uh, referring here. So then you can rewrite the first term as a omega, and then you factor out a from the first three terms on the left, and then you get omega plus b plus c. But omega is the universal set, so that includes both b and c. So the sum just omega. So then you get a times omega, which is a again. If we intersect a with the universal set, you get a. So that's equal to a plus bc, which is a union of B intersecting C. If you rewrite back into uh, uh, you know, union and intersection of sets. And remember, you have to put a parenthesis here. That's the one thing you have to be very careful because multiplication is prior to the has the priority to addition. So in terms of sets, then you have to do the intersection between B and C first. So that's why we need the parentheses here. So that's one thing that you need to be careful when you switch back and forth of those notations. Okay, let's just do some more examples. The next example is to prove a union, the complement of A intersecting C equals the omega, the universal set. Well, just do something. Change union to addition and the intersecting as product. Okay. So remember, well, I think we showed that before. You know, if you take the complement of an intersection of two sets, you get the a. I mean, yeah, you get the union of the complement of each set. Remember that? So so you have to be very careful when you take the complement. That's one thing that you need to be really, really careful. It becomes addition instead of multiplication. All right. But A and the union of A and A complement, obviously that gives you the universal set omega. And then that B complement B, it really doesn't matter because the whole thing is just omega the universal set, right? Okay, so that's one thing. That's example 3. Then the next example is to prove something more complicated. We got the 3 parts to union, and each part is the intersection. So if you try to prove it by the previous method of picking up an element on the left, it could be pretty tedious. But if you use the algebra, you know, similar in numbers, that works, and using the other results about the sets, then we can do it real quick. Okay, so so union becomes addition, and intersecting becomes multiplication. So we get ABC plus AB plus ACB. Now, you can put another AB in here on the right because AB plus AB is the same. You know, union two sets. If the two sets are same, you get the same thing, right? Okay, so then that makes it easy to handle because then we can factor out the B from the first 2 terms on the left and the factor out the B from the other 2 terms on the right. It really doesn't matter actually. left and right modification, but let's just keep it as it is. And then you get BC plus B, which is omega, and A plus AC also omega, so we get the A omega plus omega B, but any anything you intersecting with omega just that thing. So we got A plus B, which is so A union B, if you write back into Boolean algebra, right? So very straightforward. So I personally like this approach very much. So you should also use this new method when you handle the sets. It doesn't have to be, events for any sets. This is true for any sets. Okay. All right. You can also easily check, this equality is true. If you think three parts to union on the left, A, B, C, or A intersecting with B, C. So that means everything in A and not in B. Okay. So you take out the part in common for A and B in A. So that's A, B, C, right? And A intersecting B, that's the middle part. And similarly, A, C, B, just everything in B, but not in A. So you take out again the part of, in common for the two sets. So this is the right side part. Right side part. So you take the union of those three, of course, you get a union B, right? Okay, let's just do one more example about numbers. But it's really not numbers, but sets of numbers. So we're still talking about sets. So let omega be the set of non-negative real numbers from 0 to infinity, including 0. So that's the universal set, or the sample space, if you like. And we define an interval or event or set, and as close interval from 0 to 1 minus 1 over n. So that means all the numbers between 0 and the 1 over and 1 minus 1 over n, including the endpoints, where n is a natural number. Okay, any natural number. So we get a bunch of of sets or intervals, a sequence or events, right? So if there's no confusion about what space omega we're considering, which is true in here, if we just write x greater than or equal to 0, less than 1 minus 1 over n, automatically it's a subset of omega, right? So each of n, so you don't have to write the x in omega, specifically. So if you write just the x from 0 to 1 minus 1 and without omega, then everybody understand what it is. So so we can simplify this notation in the set a little bit. So if we try to take the union of all these sets, what do you get? Well, it will include 0, definitely, but you get all the part on the right side adding together. Okay, so this is the sequence of sets or intervals. That's called the net. When n is really, really large, then this right hand side will be really, really close to 1, but never be 1. So it can approach 1 as much as it can. So that's that means this right hand side has the limit of 1, but not equal to 1, not equal to 1. So all of the ANs are like this. I mean, are inside that. Okay, so if you take a union of those, then you're gonna get the interval from 0 to 1, including 0 but not including 1, right? So uh, so that's the union. And the section of n, of course, is just a 0 because when n is equal to 1, then you get the right hand side 1 minus 1 over 1 equal to 0. So x greater than or equal to 0, less than equal to 0. So that's just 1 point there. So 1 is just 1 point. So when you intersect in with all the other n's, uh, which include 0, you only get 1 point, single point, 0. So that's the intersection. Um, well, you can, use the De Morgan's law we talked about before. Uh, let's just do the complement of the union of a n first. We already got to the union of wait, a union of a n to be the half closed, half open interval from 0 to 1. So if you take the complement of it, it should be anything uh, except for that. Uh, so since we're talking about all non-negative real numbers, so that should be the interval from 1 to infinity, including 1, right? So that's what it is. Okay. The intersection of the complement of each an. So we need to find each an the complement. So what is the n? It's the closed interval from 0 to 1 minus 1 over n. So if you take the complement, it just uh, um, the the open interval from 1 minus 1 over n to infinity. 1 minus 1 over to infinity. Okay, if you take the intersection of it, um, what should you get? Uh, well, you can see each of those intervals will include 1 because it starts from a number less than 1. But when n approaches infinity, the limit of the left-hand side is just 1. So it approaches 1 from the left, but it includes 1. So uh, so this is the result will, will be 1 to infinity, including 1, because each of them include that. But um, nothing outside of 1 on the left, because that's the limit of the an, right? All right. Um, so that's what it says, x greater than 1 minus 1 over n, which is what is the interval is, means x is greater than equal to 1, right? Greater than equal to 1. Okay. So, well, we can do also the intersection of a n and take the complement. That's pretty easy because the intersection of a n for all the n's is just 0, as we just did. So take the complement of it, you get them. You just take out the 0, the point of 0 from omega, which is non-negative numbers. So that will be all the numbers from 0 to infinity, not including 0. Okay, just take out 0 from the whole thing. And the union of A and C, which is 1 minus 1 and 1 over n to infinity. Well, this part is pretty straight because when n equals to 1, you get 0 on the left. So that's from 0 to infinity. And that includes all the other n's. Okay. So that's the largest interval. And it covers all the other intervals. So the answer is just the upper interval from 0 to infinity. All right. Um, well, you can see, uh, these two things are the same, right? Uh, and they're both into from 0 to infinity. And that's what it says in the Morgan's law. If you take the union of the sets and take the complement, this should be the union of the complement of each set. And similarly, if you take the complement of the union of all the sets, it should be equal to the intersection of the complement of each set, right? From 1 to infinity. Okay, so that confirms De Morgan's law. Oh, De Morgan's laws. Any questions about this part?
No, I don't have any questions.
I think this is pretty straight. We still have 5 minutes. I think we can start the new section a little bit since this is the last class. We can do a little bit.
Okay.
Yeah. Let me just share the screen. Wait. Can you see screen?
Yes, I can.
So the section 3 is called the probability, which is the main topic for this unit. We unfortunately we don't have time left to talk about more about it, but let me just give a brief introduction, at least to define the probability in terms of sets from the mathematical point of view instead of from experiments, which are not quite precise. Okay. So we talk about um, the sample space omega. That's the set of all the outcomes in the experiment. And then we talk about the events. So each event is just subset of this sample space omega. And in a given problem, then you are talking about some events or a class of events. Okay, a particular class of events. Well, we call this class of events F, script F. Okay, so script F is a set of events. Okay, you can think of it as a set of events to form a sigma field. This set of class of events. So there are multiple events in this set. Those sets form a sigma field. What does it mean by a sigma field? Sigma, essentially, if you remember the notation, sigma notation in Cal 2, it means addition. Um, so, so this term implies, this sigma field should have some properties with the addition or union of the sets or events. In this class, we talk about the events, they are just sets. So which is a collection of subsets of omega, right? And this sigma field should follow 3 requirements. First, the sample space is one of this set. I mean, you're talking about a collection of subsets of omega. So of course, omega is subset of itself. So that's in sigma field. Okay. And the other thing is, if you have multiple events or subsets of omega, we call them A1, A2, to whatever. It implies the union of them also in this class. So F is a class of events or sets. So if you take the union of everything in this field, it should be also in this field. Okay. So that means the field, or the class is closed under finite or countable union. So that's a good important thing. Countable union. Okay, you can only talk about the countable union. If it's uncountable, comfortable, then that's not uh, well, the property. Okay, so if you remember real analysis, countable, uncountable, uncountable. For example, integers, rational numbers that are countable, but the real numbers are not countable, right? So that's the second property, and this third property means is the complement of a event in this field also is in the field. Okay, so this field is closed under complementation. All right. So from this these three properties, we can actually uh, deduce or induce some other properties. Uh, uh, so so then we can define the probability on this on these events on this field. Okay. So we assign the probability of each event a number between 0 and 1. Okay. Between 0 and 1, the probability of the sample space is 1, of course, because it always happens. So in this way, we define probability in mathematics with some properties. Okay. Uh, so in terms of mathematics, a function that assigns a number p of a to each set A in the sigma field F we just talked about, there's a collection of subsets of the omega with the three properties. And this function is called the probability measure on the field. So you can talk about the probability measure on each of those events of this class with this probability measure as a function of each event. Okay. Hey. So this is the function is the argument of the variable or the independent variable of the function is a set. So if you assign a function on each set A in this field, a number between 0 and 1, then we call probability measure. So what is the probability? It's a measure because it gives a number between 0 and 1 for each set in this field. When you learn analysis, real analysis, the measure, what's measure? It means some length or some number, right? A measure. It gives you the size of something. So here it gives you the size of the event in some sense. And the three conditions are here. So the function is always non-negative. Okay, you cannot talk about probability, negative probability, right? And the function at omega, which is also in the F, is 1. Okay, as we just said. And the other thing is if we have disjoint sets in this field F, and if you take the function value of the union of those disjoint sets, you should get the addition of each uh, probability, the probability of each event. Okay, so it should satisfy those 3 conditions. So that's a mathematical way uh, to define the probability in terms of a measure. So probability is just a measure on the event. Okay, that's what it is. So what's the difference between the other definition when we define it in terms of experiment? It gives a precise mathematical way to this concept. It's just a measure, okay, a function on the sets, and you assign, a value for the function for each of this variable a. Okay, so it just becomes a normal definition of a function, and we really don't talk about the experiments at all. But eventually, this theory you build up on probability should, of course, agree with the experimental results. But by itself, now we can give a precise definition of probability itself. So that's the difference. I guess, okay, let me just say this. Okay, I think this is important. So a probability space is a triple, including omega, F, and P, where omega is a set, that's the sample space we talked about before, the set of all the outcomes of experiment. F is a sigma field of subsets of omega. So F is a collection or class of subsets of omega that satisfying those 3 conditions, especially, the union of countable subsets in F is also in F. That's the key. That's why it's called the sigma field. And then it includes also another parameter P, the probability measure or a function defined on this field, sigma field, which gives a positive number between 0 and 1 and some properties. So this is probably so we can build a probability space on the event space. Okay. The sigma algebra or sigma field for the subsets of this sample space or event space, and then the function defined on this field or the subsets of omega. So that's called the probability space. Okay, so it includes everything that we talk about so far. And there's some basic properties of probability. The probability of empty, of course, is 0, and this can be proved easily. Okay, and there's some other properties you might have learned it before, but we don't have time to prove those things. But anyway, we just define at least the probability in a mathematical way, regardlessly. So I'm going to stop here, and